Hi guys, I want to talk about molecular orbital theory, or we'll call it MO theory, to just represent molecular orbital. Yeah, so we'll be drawing some MOs. Molecular orbital theory is a little bit different from, from our VSEPR or valence bond theory, and so this is just another competing way that we can see how atomic orbitals or molecular orbitals are going to overlap and how they interact within a molecule, or really what happens with a bond, a covalent bond in a molecule. Now, this is the last thing that we need to talk about in Chapter 9. We'll talk about or do examples of drawing MOs. We'll also do examples with hybridization, Lewis structure, all of that stuff tomorrow and Friday. So, MO theory. With valence bond theory, we know that it conveys pretty well most of the observed properties of ions and molecules, but some things are really better described by what happens with a molecular orbital. So, many characteristics for molecular orbital theory and atomic orbital theory are going to be similar. We know that we can have a maximum of 2 electrons, and they have to have opposite spins. Both hold true in molecular orbital theory and atomic orbitals. They have a definite amount of energy, so energy level is key. They have some type of an electron density distribution. But the things that are different between molecular orbital theory and atomic orbital theory is that in atomic orbitals, we really just think about one atom and how it overlaps with another atom. In molecular orbital theory, we're going to think about the entire molecule. So think about atomic orbitals as like each individual piece, and then molecular orbital theory is going to be the big picture of that overall molecule. So let's go back and think about hydrogen's atomic orbitals. So in hydrogen, I have a 1s orbital that's going to come and overlap with another 1s orbital. And when they overlap, we know that's what's creating that covalent bond. So in molecular orbital theory, we try to involve this wave-like nature of electrons. So remember we had that wave-particle duality, where a wave, we could think about electrons acting like waves, or we could also think about particles acting like, or we can think about electrons acting as particles. Or this also worked with light. So we want to think about the wave nature of electrons. Now, in a wave nature, there's something called an interference pattern. So either 2 waves can come together to interact constructively, meaning they're going to build each other up, or they're going to come together and interact destructively, meaning they're going to cancel one another out. So if I wanted to look at this as like an actual wave, maybe we should do that first before we look at these. Okay, so if I have 2 waves coming together, they both look the same, so when they come together, they're going to add up, so they're going to be constructive, and I'm going to get a bigger wave as a combination of this. So when I have 2 waves that are coming together and they add constructively, I'm just going to get a bigger wave. If I have 2 waves, so maybe this one looks like this, but the other one is the opposite to that, when these 2 come together and they're going to give me destructive interference, I'm just going to get nothing over here. They're going to cancel one another out, okay? So that's what I mean when we're talking about constructive interference and destructive interference. So for example, I can see that on my board right now, the constructive and the destructive. When these 2 atomic orbitals overlap, I could get 2 different molecular orbitals. So one of the molecular orbitals I can get is when it's a constructive interference, meaning that they're going to come together, build one another up. So that's this one. Because this is a head-to-head overlap, I see that the covalent bond would be between the 2 nuclei. It would be a sigma bond. So we call this one just sigma. So this particular constructive interference, or the constructive interaction that we have between this atomic orbital and this one, is going to make a sigma molecular orbital here. I could also have another one, which is called the destructive interference. We're going to call that one sigma star. So I'm going to put a little asterisk next to the sigma up in the superscript on the right-hand side. So this is constructive, and this is destructive. So destructive is going to create just this empty region in between those two nuclei, or we can also call that the nodal plane. So destructive means anti-bonding, and then constructive interference is going to lead to a bonding orbital. Which one do you think would be most or more energetic? The one that will lead to bonding or the one that will lead to anti-bonding? If you think about this, most atoms would prefer to bond. A lot of times sharing an electron will make them more stable, so that way they can fulfill that octet. So our bonding molecular orbital is more stable here. So sigma doesn't have the star because it's the bonding. Anti-bonding, which is the destructive interference, anti-bonding is going to be more energetic because electrons really don't want to be in that type of orbital, because that's indicating then that there's a higher energy. These are probably more energetic electrons then, so that atom has been excited and it's not really in like its ground state, okay? So constructive, sigma, and bonding, anti-bonding, destructive, we'll call that sigma star. So this just says if waves interact destructively, the resulting orbital is higher in energy, and we call that an anti-bonding molecular orbital. So how would I draw this? If you're wanting to draw a molecular orbital, I'm going to draw, let's say, for example, we want to draw it for hydrogen molecule. I know that I'm going to have a hydrogen atom, and that's going to interact with another hydrogen atom. So each of these hydrogen atoms, I look at my periodic table, I know that hydrogen has one electron. So I fill in, just like an orbital diagram, this one electron here, and the other hydrogen is going to give an electron in the opposite spin, and that's going to be, so here's my 1s, here's my 1s over here. Bonding orbital is going to be lower in energy than the atomic orbitals. Anti-bonding orbital is going to be higher in energy than the atomic orbitals. So ultimately, I just want to fill in these molecular orbitals, which are here and here, down below. Here's my bonding, I call that sigma. Here's my anti-bonding, I call that sigma star. So I have one coming from here, I fill that into the lowest in energy. So think about Aufbau principle. I want to fill lowest energy levels first. So this electron is going to come and fill in this one. This electron is going to fill in this one because an orbital can only hold 2 electrons, and I'm done. So this is my molecular orbital or my MO for the hydrogen molecule. And I can see that it's stable because both of the electrons are in the bonding orbital, okay? So in H2, 2 electrons go in the bonding molecular orbital. We also want to get into something called the bond order. And the bond order is 1/2 the difference between the number of bonding and then the number of anti-bonding electrons.